Excellent. I think that did it.
Okay.
Now they're going to hear us talking about this.
Can you tell?
No.
Did we start it?
Let's keep it. Yeah,
Start. Okay, so it works.
I think we're good.
Okay.
Julius, can you check this?
Yeah. Are we good? Okay. Cool. All right, so I think we're good now. Sorry for that interruption. So just to reiterate, yeah, essentially reinforcement learning is the art of goal-based learning. So the goal of this type of learning is to take some form, teach your agent to take intelligent actions so that you optimize rewards that you specify that lead you to some goal based on the information that some agent knows about the current environment. And so this is different from kind of deep learning, where if you imagine in deep learning, you have some, the goal is usually to do like either classification or regression or feature extraction. And so to train like a deep neural network, the only information you get is whether, based on some input you get, whether you predicted essentially like something close to the correct output. Whereas in reinforcement learning, for any action you take, you don't really get like, there's no sense that the action was correct or not. There's just a sense that some actions are better than others. And the way you compare that is based on rewards that are specified by the programmer that tell you whether an action is good or not. If this is all very abstract, I'll try to get more into a concrete example later on. Hopefully that will clarify things. But below are just some examples of like where you could apply reinforcement learning. So in a self-driving car or in a simulation when you're trying to play a game or trying to play against a human player in a game like Go or chess, you would use like a reinforcement learning system. And so I kind of mentioned some of these terms. The basic framework of reinforcement learning is that you have some kind of agent. It's a learning agent, some kind of intelligent agent. And the agent performs actions that affect the environment around it. And based on those actions, it perturbs the environment, and then the environment gives it some form of feedback, which in this case would be the rewards, and then observations that the agent is able to observe. And so there's this kind of, you can see there's this kind of artificial boundary you can draw between like agent and environment, where you can think of it as an agent as everything that's directly controlled. That this agent, everything on the left side of the boundary is everything the agent can directly control with its actions. So that would be akin to something, if you were to actually code this up, everything that you could actually specify and tell the agent to directly do. And then the environment would be everything that's outside of your control. And so just to talk about kinds of environments you usually find your agent in, and stop me at any time if there's like, if I'm going too fast or if you have any questions or anything's confusing. But to talk about two different kinds of environments that an agent would find itself in. Usually you can break it up into what are called episodic and continuous environments. And so these kinds of, the episodic environment is basically where this interaction between the agent and environment, where an agent performs an action, the environment gives it feedback, and then the loop continues. These interactions can be broken up into finite time steps. And so for basically the agent would interact with the environment for some number of time steps, and then the episode would reset. And so you can think of this, again, going back to the Atari example, as you say you're trying to train an agent to play this game. Well, the game essentially ends when either you win and you knock out all the blocks on the top, or the ball falls past the screen. And so after the game ends, the environment will reset, but the agent will keep its experience. And so to train this agent, you basically just have it play multiple episodes, multiple rounds of this game to have it learn. And so it's easier to think about things in terms of episodes because they're discrete and they're finite time steps. But in a lot of real-world cases, environments are essentially continuous. And so basically the agent never has the chance to like stop and reset its state. So for example, in the real world, if you have a car in a self-driving car fleet, this agent has to continuously learn and update on the fly. essentially. There's no natural sense of when you would really stop an episode of driving. The car is just, driving along a road, and it's just going through the environment. And so this form of environment is usually more difficult to train, just because there's no, it's like an infinite, there's no sense of like when you would stop the loop. So typically we think of things as episodes. And so kind of as a motivating example for like a very simple agent, let's imagine, I'll talk about like what these actions and states and rewards are. Basically, imagine you have some kind of robot, like a Roomba or something, that's trying to navigate in like a grid-like environment. We call this like a grid world. And so the goal of the robot is it's placed somewhere in this maze, and then it tries to escape from the opening at the top right. And so to do this, in the beginning, so keep in mind that the agent probably, if this was a real like robot, it probably doesn't know the whole layout of the maze. Like it doesn't know that every path that it can take to get to the end. It really just only knows its immediate surroundings. And so to figure out the best kind of thing to do, it essentially has to take random actions or just actions and then see what happens and then see whether it gets put in a good spot or a bad spot. And then based on those actions, based on these rewards and the states it gets put in, it has to kind of either figure out like a representation of the environment it's in and then kind of try to perform the best actions for any given situation to, in this case, get it towards this goal, where the goal in this case is, moving out of the maze. So it helps to think of this problem. Just based on this, it might not be clear how we do any of these things. And so some of the questions you might have about this kind of scenario is like, what exactly can the agent learn about the state of its environment? Like, does it know everything? Does it know just local information? How does it get this information? What kind of actions can your agent actually take? Of course, you have to know which actions are better than others. So how are those actions rewarded over time? And then finally, you have to know, based on an action you take, how does the environment itself change or transition? So I'll just go through each of these questions one by one, and hopefully you'll have a better understanding of the whole problem in the end. Yeah, so first, what does the agent know about the state of the environment? Well, basically, as a simple answer for a physical robot, what the agent knows is essentially what its sensors are able to perceive. And so we define essentially an observation as anything an agent is able to perceive about an environment. So if you're a robot, you might like have a camera sensor on the front of your robot, and so you might be able to see everything that's in front of you. Or you could have like a depth sensor that senses things that are close to you, and so you might have like a local map of like your immediately surrounding area. And so you can think of those observations as just raw data. It's just a perception, as if for a human it would be like what you can see, hear, feel, and touch with your five senses. But for a robot, it would be what you get from the sensors. But of course, that kind of raw data might not be useful because that kind of data, if you think about input data from the camera, those are just pixel values. So the learning algorithm, really has no way to intuitively know what those pixels might represent. And so we want a way to transform this kind of observation that an agent has into a better, we want to extract important features from that observation so that the agent actually learns the important things about the environment. And so we call those features, or like the relevant information that an agent can extract, the state of the environment. And then we call this set of all possible observations, or the set of all possible states, the observation or the state space. And we usually denote the state space with like a capital letter S. So like in this diagram, you can kind of think of the state space as like a higher level representation or a subset that is extracted from the observation space. So as an example for the grid world I was talking about, a very simple state representation might just be the number of walls in this discrete setting, the number of walls like immediately surrounding a robot. So in this case, there's 3 walls. Like if the agent was, I guess, in this position, if you can see my mouse, there would be 3 walls surrounding it, and so that would be the state. And so you would have, because there would be, for each wall, you could either have a wall or not have a wall next to it. There would be 16 possible configurations for that state. And so that's like a very simple representation, but there are actually like problems we run into when we think about state space. types of representations we can use. And so if you think about it, I just said that state was kind of like a higher level representation that extracts features from those environments. But that doesn't guarantee that two states that each unique location will correspond to a unique state. So what exactly do I mean by that? Well, if you take this magenta square and this orange square, you can see that based according to this first representation, they would have the exact same state. There's a wall above it, or north of it, and then a wall south of it. But they're in different locations. And the actions the agent will want to take to reach its ultimate goal are exactly opposite of each other. In the left case, it would want to turn right immediately, or to the east. And then in the orange case, it would want to turn to the west. And so I'll talk a little bit more about this when I get to how we think about actions the agent takes. But just keep in mind that this kind of state, we call this state aliasing, when the same state represents two different locations. And this kind of thing kind of interferes with the agent's ability to learn important policies. And so one method to solve that problem might just be that instead of having the state be the number of walls, we have it be, if we assume that the agent is only in this bound grid box, we assume that we give each block a number. Each block the agent can traverse a number, and then use that as the state. So in this case, because there's I think it's a 10 by 10 square, there would be 100 different states. But you might already see the problem with this, which is that for larger environments, and just as the state space gets more complex, the number of states is going to explode. So if you double the size of this area that the agent was trying to traverse, then you end up with 4 times the number of states. And so this really isn't a great representation in that sense, although it does solve the state aliasing problem. And so there's kind of, I guess the main thing to take away here is that whenever you think about a state that you're trying to define for an agent, there's always a trade-off between how complex the representation is, and then how big it is and how efficient it is to compute. Okay, so we talked about state. What about how the agent, so given information the agent learns, what actions can it actually take? And we call basically these actions, if you caught the gist here, essentially the state and the actions are all defined by the programmer. You can define your environment and your agent to be whatever is useful to mimic the actual environment the agent is in. And so we call the set of all possible actions that you define for an agent as the action space, which we define by a capital A. And the goal of the agent, in order to reach this goal, is to learn a mapping, or what we call a policy, so that for a given state that it knows it's in, it outputs an action that lets it get more towards this goal. And we define the policy function with a letter pi. So it maps between the set of all states to the set of all actions, and then for a given state, it'll take one of many possible actions. So this policy function is really, you can think of it as kind of almost like the brain of the agent. It's essentially what's making the decisions and telling the agent when to take a certain action in a certain location. So for the grid world, a very simple action space might just be, you can move in one of 4 directions, one of the 4 cardinal directions, and then a policy might be, for a given state, if I'm in this northbound corridor, move north with probably 100%. If I'm in a corner, move north or move east, each with probably 0.5 or 0.5, and then et cetera, for each of the possible states. And so you might notice that here I said that here the policy for a given state might output a single action. So that would be true for a deterministic policy, but for some cases you would actually want to have a policy that maps from a state to a probability distribution of actions. So it would give kind of a confidence that this action is a good action to take. So here it would say, in this case it would say oh, I think half of the time you should move north and then half of the time you should move east. And so you might be wondering why we won't just have, if we do enough training, surely we can find a deterministic policy that would move the agent towards its goal for a given state. And so one of the advantages of having policies that are defined in terms of probabilities, yeah. Mm-hmm.
Is there a higher probability to move east into the wall than east to move west?
Oh, so that was basically I just made these probabilities up. So it would really, those aren't real learned probabilities. Yeah, in this case, it would probably make more sense to have a 0.5 probability for each. But I just wanted to show that Like there's no, you don't have to have the probability be equal among all the actions. Yeah. It really just depends on how you learn the probabilities for each policy. Does that make sense?
Well, you made a mistake.
Oh yeah, sorry. There's a typo there. You could, so yeah, technically you could go east, but depending, like if you define the environment, then like that wouldn't be a good thing. Yeah. Yeah, thanks for the catch. So why do we define things in terms of probabilities? One of the reasons is that it helps you break out of the state aliasing problem. And so if you learn just a policy that outputted a single action for each state, then for the state where it was in a top wall, or where there's a wall to the north and to the south, if the agent was in this state on the left-hand side, then it would always move away from the goal. And so the decision would be correct, to move left if it was on the right, but for the agent on the left, that wouldn't be correct. But if we define things in terms of probabilities instead, then at least some of the time, the agent, if we perform the same experiment and put the agent in the griddle multiple times, if we perform the same experiment multiple times, at least some of the time, the agent will move towards the goal correctly. And so this isn't a complete solution. State aliasing is still just kind of a problem. And so I guess really a better solution would be just to find a better representation of the state that's efficient to compute, but also gives you a lot of information about the environment. But yeah. So it's not a complete solution. And it's not a completely solved problem either. So given actions you can take, how do you know which actions are better than others? So far I've just talked about assuming you have a policy, how the policy will make the agent move. But we have to actually learn these policies before we can use them. So the way, in order to learn them, we basically just define a measure, an instantaneous measure of how good an action is. We call this measure a reward. So it's just a real number. Usually, there's not really a bound, but it's just like a finite real number that we assign to every action in a given state. And so you could say, great, maybe we can just use these rewards. I take an action, it gives me a reward, like a treat, and that's great. I can use this to learn a policy. But the problem is that sometimes you want to think not just in terms of a single action, but sequences of actions. And so an action that you take that is good at a specific time point might lead to a state that ends up being worse for you in the long run. And so instead of thinking just in terms of rewards, we want to think in terms of sums of rewards in the future. And so we define sums of future rewards as a return. And here I say it's defined as the discounted sum of future rewards. I'll explain what that means on the next slide. But in general, a return is basically just a measure of how good a sequence of actions, or how good an action would be in terms of how much reward you would get for like k time steps in the future. And then finally, we define this thing called a value function, which we'll use later on to learn a policy. And a value function is essentially a function that for each state gives you an expected value of a return that you would receive from that state. So on average, if I were in this state, how much value should I expect to get? And so if you have this kind of value function, it essentially allows you to compare different states. And so you could say that a state is better than another state if it has a higher value or a higher expected return. So yeah, there's a lot of math on this slide, but basically these are just definitions mathematically of each of the terms I defined below. Reward is basically a function where, based on a state and action that you take, it outputs at each time step, which is why you have the subscript t, a capital R, which stands for a reward that you would get at a specific time step. And so based on this reward that we get, we can define the return as a sum of all these rewards. And so you notice that there's like this we call this the discount factor. There's this value gamma. Yeah. And so this gamma is just a value between 0 and 1. And you can think of it as like a weight that tells you how much you should care about the future. So if you notice, because gamma is between 0 and 1, the value, the rewards, the amount that the future rewards affect the return diminishes as you go further in the future. So future rewards, you don't care as much about future rewards as you care about present rewards. And the higher you make this gamma, the lower you make this gamma, the less you care about the future. And the higher you make the gamma, the more you care about the future. And then finally, you can write returns. So this is just a recursive formulation that makes things easier on the eyes. You can write returns as sums of future returns. So if you notice this RT plus 2 plus gamma, if you factor out a gamma here, then you're left with G of t plus 1. And then for value functions, so here I said there are functions mapping states to expected returns. More generally, you can also think, so if it maps a state to an expected return, we call it a state value function. But you might also want to know the value of taking an action in a given state. And so if you think of the value of that, we call those action value functions. Each of these are defined essentially the same. They're the expected value of the return, which we just define as gt, given either that you're in a state S or given that you're in a state S and you take an action A. And then here we just write it as a sum from 0 to the future. And notice that this expected value, there's this little subscript pi. Basically, that just means how much value you get if you follow a specific policy. So whenever you think about value functions, you kind of have to think about them in terms of policies. You can't just say what's the value of the state, because that would change depending on what action you would take in that state for a given time. And then, well, first, did that kind of make sense? Any questions so far? Okay. Cool. So they're defined as functions, but if we have a discrete number of states and actions, usually it's easier to just define them as tables. So if you have a finite amount of states, going back to the grid world example, here I have 8 states, but imagine you had like 100 states. Then for each of those states, you could store the value in an array. So this square would represent the expected value, or the value that you get when you start in state 5 going forward. And then you can do the same thing for this cube. Oh, sorry. One notation thing I forgot to mention is that for state value functions, we typically use either lowercase or uppercase v's. And then for action value functions, we just use q's, uppercase or lowercase. And that's just a notation, a convenient notation that we use to make things consistent. But for action value functions, we typically map it as a table. And so each cell in the table represents the return when you're in a given state and you take a specific action. And so this just makes things, so to query like the actual table, if you wanted a specific value, you can just pass in an index or a set of indexes. And so this just makes things easier when you have a finite set of actions and a finite set of states. Yeah, and so that's generally how you define rewards for different things. But sometimes, so I've been talking about rewards as if they're kind of, the be-all, end-all, as if like if you define the reward, then if the agent, gets as much reward as possible, it'll naturally just follow a policy that'll get it to the goal, and like we're all fine. But that's actually not true. So remember that the reward is defined by the programmer. So if you define the reward incorrectly, then the agent will do some kind of behavior that you don't want it to do. And so in this example, if this game is a boat race where you're trying to go around. You might have already noticed the agent is doing something weird. Yeah, so what we want it to do is to follow those other blue dots and go around the race. But the way they define the reward is that if you collect fuel canisters, which gives you like a turbo boost, then it also gets reward. And so because these turbo canisters in this game happen to respawn conveniently, like every 3 seconds, the agent just kind of learned a policy where it can just do a loop-de-loop and continuously get fuel canisters instead of going to the actual goal. Yeah, so this will basically just keep happening ad infinitum until it either crashes or the world sucks. So the point here being that you really have to be careful about what kind of rewards you define. This was research, by the way, if you're interested, done by OpenAI in faulty rewards. And so this is kind of like a really important research topic in that how you define the rewards really changes the behavior of the learning algorithm. And it's just funny to watch. So anyway. Yeah. So that was the rewards. Finally, we also want to know how the environment will transition between different states. So once you give it an action and you get a reward, do you know or do you not know what next state you will be? And so we kind of model this as a probability. So this is the key. We call this the state transition function. And just kind of to break down this notation, forget about the R for a second. It's just a reward. But essentially, it gives you the probability, given that you're in a specific state and you took a specific action, that you transition to a next state, S prime, which is also in your state space. And then we can also model the probability, either jointly or separately, of getting a specific reward at a time. And so we call this a state transition function or a model of your environment. And so if you know the state transition function, then essentially you could run through a simulation of your environment, and then based on your actions, you could continuously compute probability of the next state, sample from this function, and then do training. And so I've been talking, in the examples before, I've been talking about a physical environment mostly, where you have an actual robot, and to train it, you would actually have to like plop it in an environment, have it try to go to the goal, and then reset the experiment once it stops, and continuously do that. But if you have a model of how your environment reacts, if you think about it, you don't really need to actually do the training in the environment. Instead, you can use a simulation of your environment if you have a model, and that'll speed up training because you don't have to worry about problems that happen in the physical world. And you can also parallelize your training by training multiple models at the same time. And so if it uses this model, or if the agent has access to this model, we usually call this model-based reinforcement learning. And if it doesn't, we call this model-free reinforcement learning. OK, so now we've kind of answered a lot of the questions about how you define different problems in this reinforcement learning framework. So just to recap everything one more time, try to bring it all back together. In general, you have an agent and it interacts with an environment. The agent has access to a state of the environment, and then based on that state, it'll take specific actions that perturb the environment, and then that'll give it, the environment will give it back a reward in the next state that it's in. And then the agent will update its policy and then also usually its value function to get a better model of what states and actions are good. And so I haven't really talked about training, how you actually train policies or value functions. We'll get to that in just a second. But before that, I want to talk about one more problem that is pretty key to the idea of reinforcement learning and goal-based learning. And so this is the idea of what we call exploration for exploitation. And so I kind of like to, this kind of analogy came to me one day, and I think it kind of makes sense. I kind of like to think of it in terms of story of Morpheus from The Matrix, for those of you who have seen The Matrix. If you haven't seen The Matrix, basically the idea is that the main character is offered a choice between two different pills at the start of the movie, red pill and the blue pill. And so Morpheus tells him, if you take the blue pill, story ends, you wake up in your bed, believe whatever you want to believe. It's kind of a safe choice. If you take the red pill, you stay in Wonderland. I'll show you how deep the rabbit hole goes. And so you can think of tying this back into an agent learning in an environment. In the very beginning, the agent really has no idea of what actions are doing. It has to learn the same time. And so as it kind of goes along its rabbit hole, goes along its path, it learns some actions that seem to perform better than the actions it's seen. So among the small set of actions that it's taken, some of these actions are clearly the best. And so at this point, it still hasn't explored most of the action space, but it might just say, it's good enough. I don't want to risk getting lower reward by taking new actions. So I just want to take the safe route and just kind of continuously, now that I have kind of a rough idea of some of the good actions I can take, I just want to continuously take a good action I've taken before and continuously just get a fairly good reward, even though there might be a lot better rewards that I don't know about. So you can think of that as exploitation, or taking the blue pill, the safe route. And the advantage of this is that that's the only way that you can take advantage of past experience. Because if you continuously explore and take new actions and never go back to the ones that you've learned, there's essentially no point in having the experience in the first place. You might as well just take actions randomly. But the problem with just exploiting something is that you might not know all of the actions, the true story of all the actions that you can take. So some actions that you haven't taken might be a lot better, or like a previous action you've taken might be better on a second try. And so in general, for reinforcement learning, you have to balance actions, exploration, and exploitation through some kind of method. specifically in the context of in your policy. Even if you have a deterministic policy, or like a probabilistic but a very close to deterministic policy. And so the way we do this is through something called epsilon greedy methods. And so for a normal algorithm, usually what you do is based on a value function or policy, you choose the action that gives you the best value. That, I hope, intuitively makes sense. But of course, that doesn't let you explore new actions. And so a small tweak or modification you can make to change what you do when you use your policy is that most of the time, with some probability 1 minus a small value epsilon, you take the action, so the argmax over A of your value function. You take, given a state, you take the action that maximizes your value. You do that most of the time. But then, with some small probability epsilon, you choose just a completely random action out of the blue. You decide, whatever, I just want to try something new, I take a new action. Sometimes that action may pay off, sometimes it hasn't, but at least now you've explored more of the actions you take. And so in the special case when epsilon is 0, we call that greedy action selection. That's generally what I've been talking about when I talk about policies previously. And so in general, if you take larger epsilon values, then you'll explore actions more quickly because you're acting more randomly. But if your epsilon is too large, you're doing the same thing as akin to random action selection. But as you take a smaller epsilon, non-zero epsilon, you're exploring very little. So most of the time, you're taking the optimal action with a higher probability, but you're still exploring all the actions you can take. And so in this case, you can kind of see like, this is an agent trained on like a lottery to optimize rewards on a lottery machine, essentially. The task isn't as important. But basically, you can see that in the beginning, if you specify higher epsilon, the agent learns faster. But the smaller epsilon, based on this trend, given enough time, will actually outperform this other agent. And then the greedy agent it chooses an action that it thinks is best in the beginning, and then it never learns to explore the rest of the action space. And so it performs much worse than the other two. Okay. Any questions on anything? Cool. So, we've talked about how to define the problem. We've talked about exploring action spaces and state spaces, but we haven't really talked about how the value function and the policy kind of relate to each other, at least not in detail. And so, to actually train and learn good policies and value functions, well, let me talk about this first. So, if you have a value function that tells you how good a given policy is, then you can use that value function to compare different policies and find, so if an agent wants to choose the best policy, it can just choose the policy that maximizes the value it gets for a given state. But of course, we don't actually have a value function or a policy in the beginning, because if we did, then it wouldn't really be a problem. It wouldn't really be a reinforcement learning problem. Generally, the agent has to learn both a good policy and a good notion of what actions are good. And so there are kind of two questions we have to answer in order to kind of train agents correctly. The first is, for a policy, how do we get an idea of how good the policy is? How do we learn a correct value function? And then the second problem is, just because we have the policy, how do we move to policies that are better than the current policy? And so it turns out that we actually use the value function for the policy we originally had to kind of create new policies that are better. We kind of iterate on the policy we have slightly after in kind of a policy improvement spectrum method. And this so learning value functions for policy is called policy evaluation, and then improving policies is called policy improvement. And both of these are steps in something called generalized policy iteration. If it's too long to say, you can just say GPI. That's the general abbreviation. And so the general algorithm of GPI is that you find value functions for a policy, and then based on that value function, you improve the policy, and then you repeat this process ad infinitum until it converges to an optimal policy. So these are two graphs that I stole from a reinforcement learning textbook that I found was really useful to kind of understand this procedure. You can think of this pi and this v as both estimates of some kind of optimal policy and value function. So pi star here is the best policy you could possibly have among all possible policies. And v star is the value function for that policy. And so even though these are both estimates, we can basically assume this is a good estimate of the optimal value, and then use it to better improve the policy. And then do the same thing in reverse. Use the policy to improve the value function. And do this in a cycle. And what this ends up doing is you can think of these two lines as kind of two axes of convergence. So as you get closer to the optimal, as you improve the policy, you kind of like zigzag along these two lines. Improving the value function helps move you closer to a better policy and vice versa. And so you can zigzag along these two lines of improvement, evaluation and improvement, until you finally get to some optimal policy. And that ends up being a lot of how we train reinforcement learning algorithms. There are like different iterations and different kind of changes you can make, tweaks you can make, but this is the general framework. So I'll just briefly talk about these two, how you do each of these. So for policy evaluation, given a policy pi, you can typically do one of two things to update the value function. You can do what's called a sample update, or you can do what's called an expected update. So the idea behind these is both the same. In both of these, you basically explore some environment that you have for k time steps using a policy. You collect all the rewards you see along the way, and then based on those rewards, you update your value function to get a better idea of what it is. And so this diagram kind of explains a little bit. We call, every time you move along a specific set of states and actions and rewards, we call that a sample or just a trajectory. And so you could imagine if we take state, let's say this is action 1, action 2. If we take action 2, we get some reward, and we come to this white circle state S prime. And then we do this again for another time step. We take another action, say this time we take action 1. We get another reward, and then we arrive at some other time step. And then based on the sequence of rewards we get, at the end we reach some other state, and then we use that all to update our value function. So that's called a sample update. For an expected update, it's basically the same thing, except you kind of do like a thought experiment. So if you have access to a model of the environment, you can kind of think about what would happen, because you have access to this P here in this diagram, which is the probability of transitioning. You can think about, with some given probability, I will transition to this next state by taking an action. And then based on that, you do the same thing, and you follow a trajectory downwards. So you can think of it as following multiple trajectories and then doing like a weighted sum of all those trajectories using the probabilities. But then you do the same thing. You update the value function with that expected value. And so an example of like a sample update you could do, basically the method that people use a lot when they talk about like getting started in reinforcement learning is called Q-learning. And so this is akin to what I was talking about, how you actually update the value function. And basically this is the heart of reinforcement learning. So if you understand anything else aside from environments and agents, you should probably get to know this a bit. So to explain this a little bit more, I like to think about this in terms of like, for deep learning, a gradient update. So you have your original value estimate of value, that's state S and A, and then you add to it times, you multiply by some learning rate, not really a gradient, but like an update of the new value you want Q to take. And so to look at this like pseudo gradient, let's call it, we call this a temporal difference update. And the reason we call it a temporal difference update is because this is what happens when we look one step ahead and then use the reward we got to update the original value estimate. So there's two parts to this. The first part is this term, which is R plus the discount rate gamma times the maximum over all actions that you could take of your value. So to say that in plainer English, it's essentially, you can think of that as the return you would get if you took an action, if you just took your given action, and then you took the best action, and you reached your next state S prime, and then you took the best action that you could take given what you know, for like following further. And so you subtract this value from like your original value. So this gives you like a better estimate of like your value in state S and A. And then you subtract that from your original value estimate. And that gives you like a gradient update of sorts. So If that didn't really make sense, I can say it one more time. But that's the general idea of this update. It might take a little while to get used to like the math and the notation, but if you have questions, you can also come ask me afterwards. We'd be happy to explain it again. And so that's just one form of update you can do. But you can also do lots of other updates. And so the general idea, so this is one example of an update that I explained. But the general idea of an update is that you follow a trajectory of actions and states down several time steps, like 3 time steps. And then based on whatever state you arrive in, you estimate the value, the return you would get from that state that you're going to end up in. And so because, if you notice in this equation, this Q is actually just an estimate of the return you get. So we're essentially updating an estimate with an estimate. And so that kind of idea is basically just called bootstrapping. The idea being that even though all the estimates are pretty bad in the beginning, as you update them with slightly better information, the entire value function will improve. Even though it's not like, you're not using the optimal value function to update it, it's still getting better incrementally. And so basically you can do, I just talked about Q-learning, but you can do like any number of updates based on how many time steps down you go, and then how many trajectories you look at. So on the left, I have an example of a sample trajectory where you follow a specific path down to a state. And on the right, I have an example of an expected trajectory. You kind of think about, oh, if I took this action, I would get this amount of reward. Or if I took this other action, I would get a different amount of reward. And then you do a weighted sum of both. And so this gives you the point here being that this gives you a lot of flexibility in how you actually update your value function. You're not stuck to just taking this specific equation. You can tweak it by changing how many time steps you enroll, and then how many trajectories you look at. And then once you're given, once you finally like reach an optimal value function for a policy, then given a value function, you can now define a better policy than the one you currently followed by taking the maximum, defining the policy as the maximum for each state, the action that gives you the maximum value for each state, essentially. So it's really this is just a really simple equation. The idea being that just because a policy gives you a value doesn't mean it's the best policy for that value function. And so if you can find a better policy, then why not go ahead and use it? The problem here being that once you use that new policy, the value function isn't like accurate anymore because that value function was for your old policy. And so you can improve like your entire process again by doing another round of policy evaluation and then policy improvement. Yeah. So just to reiterate, the general process is like it sounds very circular, but it ends up working. You find a value function. You start with a random policy. You find the value function that corresponds to that policy, and then you find a better policy based on that value function. Cool. And then, so that was most of what I'm going to talk about in terms of reinforcement learning. Just for the last couple of slides, I want to kind of tie in what we talked about with deep learning and how we can apply it to reinforcement learning. Because it turns out there's a really big problem with reinforcement learning in terms of how it scales. Specifically, as you increase the number of states and you increase the number of actions in your problem, you run into this thing called the curse of dimensionality, which I forgot to mention verbally, but I had on the slides. But essentially, this curse of dimensionality basically states that the size of in terms of reinforcement learning, as the number of states and actions increase, the size of your state space, of course, by definition, will increase. The size of your table that we're using to map values will also increase. And then your policy, the amount of storage you need to map your policy will also increase. And so this isn't just a problem in terms of storage. This is also a problem in terms of training. Because the more states you have and the more actions, the more times you have to go through your environment to visit all those states and actions to get a better sense of how good your value is for them. And so if you think that's bad, because of this multiplication, like try thinking not in terms of discrete actions and states, but what if you could have a continuous state space? So what if your state space was not just a cell, but it was like a specific geographic coordinate in a room, like an x coordinate and a y coordinate? Then you could have an infinite number of states and then you could also possibly have an infinite number of actions. And so this really gets out of hand. Like, there's no way to store an infinite number of actions and states in this table. And so just as a side note, what people usually do to approximate like continuous state and action spaces is kind of like, they partition the state space into like discrete dimensions, and then they kind of like use that lower dimensional representation, and they like kind of they turn a continuous state space and action space into discrete state and action spaces. And then you can reduce the problem to the same methods we just talked about. But I won't mention that too much right now. But the point here being that it would be nice instead if you could use deep learning as a function approximator. So instead of representing values and policies, as tables, why not actually just represent them as functions or approximation of functions? And so in general, there are a couple of things you can use deep learning for to couple reinforcement learning. The first being that you can approximate both the value function and the policy. And the second advantage of this is that because deep learning, like neural networks are good at performing interpolation between two states that they've seen, you can kind of interpolate, I say extrapolate, but interpolate from states and actions that you've seen to do a mapping to states and action pairs that you haven't seen. And of course, the additional advantage here being that even if it doesn't give you a good solution, it at least is a defined, like it'll output something, as opposed to a table where you will literally have an undefined representation if you haven't actually seen the state or the action, or perform the action. And then finally, you can use deep learning as a state, like a feature extractor. So I talked before about using camera images as sensor data. This fits very nicely into the convolutional paradigm, where you could feed an image through a convolutional neural network and then have it return a low-dimensional, or just a state representation of the pixels in that image. And then feed that in as a state to another network that you train to learn either a policy or a value function, or both. Yeah, so in conclusion, reinforcement learning has done a lot of cool things in the past couple of years. It's kind of like, it's still a very big research field. DeepMind, I think, and OpenAI are doing a lot of research into it. Obviously, there's applications for like self-driving cars. If you've heard of AlphaGo, which I showed a picture of in the first slide, or second slide, it beat the #1 Go player, I believe in, I forget the date, 2014, 16. I'm bad with dates, but pretty recently, within the past 4 years. And so there's a lot of promise with these reinforcement learning, using reinforcement learning. So I encourage you to explore more through either. I found that these resources were really helpful. Introduction to Reinforcement Learning textbook by Slutto and Barton. That was kind of like a seminal. I still see it cited a lot in like reinforcement learning papers. David Silver's Reinforcement Learning lecturers, David Silver was one of the people who worked at DeepMind. I find that his lectures are, one, I like listening to his accent, and then second, I find that like he does a really good job of kind of just explaining the basic concepts. Yeah. Also, yeah. Yes. Actually, was it?
Yes.
Do you mind? Okay. Okay, I forget. But yeah, David Silver's RL lectures are good for that, for learning. And then finally, just a resource. If you want to like find more videos about the faulty reward function that I linked, you can go to the OpenAI blog. Yeah. So that was all I had. Shout out to our sponsors. One last thing, there'll be a paper discussion tomorrow. Devin will be presenting on neural evolution, which is tangentially related to reinforcement learning, but it's kind of just like another topic. That's pretty exciting and cool. So you should definitely come by and check it out. 7 to 8 tomorrow in Hawaii. Our next workshop will be next Wednesday. The topic is yet to be determined. We'll get back to you with an email. And then finally, if you're interested in just hearing talks from other important people in the field of machine learning, the MIC community is holding a conference this November 3rd, so this Saturday and Sunday at the MIT Media Lab across the river. Walk-in registrations were closed for a couple of weeks, I think. But if you walk in, we should have more than enough space to accommodate you. So if you're interested, you should definitely drop by at least for a couple of talks. It'll be a pretty good conference. Yeah. That was it. Thanks for coming. And as always, if you have any questions, I'll be around, so feel free to ask. And there's more pizza. So take it, please. Yeah. How do wait, I might have closed the box. What the heck is going on?
Close that. Yes.
Which are you mean just the reward? I stopped the stream. You're fine.